Hey everyone, Mike here from ArnoldTutoring.com with a good proof question in calculus. It says if f prime of x is less than 0 for all x in AB, so some interval AB, prove that f of x is decreasing on that same interval. So a couple things going on here, but the first is to realize that they're talking about first derivatives and decreasing. This might even be part of a bigger question where they actually give you a hint of what theorem to use to prove, but what it's going to be is the mean value theorem. So there's another video that explains what the mean value theorem is, but I'll quickly go over it again. It says that if a function is continuous and differentiable over an interval AB, then we have some point in between A and B called called point C. The derivative at point C, or the slope of the tangent there, is going to be the same as the slope between the two endpoints. So that's a quick review of what the mean value theorem is. Again, there's another video on that. Let's see what we have to prove here. We have to prove that f of x is decreasing over this interval. So I've labeled 2 points here. Let's call them. Here's the x values a and b. So this point here is a f of a, right? F of a is just the y value at a. And this point is b f of b. So I've drawn them as if they are, it is obviously decreasing here, but we're trying to prove that it's decreasing all the way through the interval. So it could, it could technically go up like that, but we're going to prove that it can't. So what do we need to show? We need to show, well, we need to show a being less than b. A is the first x value and b is the larger one. But then we need to show that f of a is actually larger than f of b. This is what we're trying to show. So we're going to assume this and try and show this. Okay, so what do we have to do? Well, we're told that f prime of x is less than 0 for the entire interval. So that already checks our first two boxes of the mean value theorem. So we know that f of x is continuous, because if a function is differentiable, it's continuous. So it's continuous on AB, closed interval, and we already it's telling us that it's differentiable. In other words, we can take the derivative everywhere on AB. So that's good. Once those two are held, it means this must hold. Okay, so we can then say, I'll just write the theorem one more time, f of b minus f of a over b minus a equals this f prime of c, where again c is some point between a and b where the slope of the tangent will match the slope of between the endpoints. If we cross multiply here, just multiply b minus a to the top of the other side, what have we got here? We've got f prime of c times b minus a. Well, remember the two things we've already assumed. We've assumed this, and we've been told that f prime of x is negative, right? We've been told that it's less than 0. So we can think of this as f prime of c is a negative. We don't know what the number is, but we know it's negative because we've been told. And b minus a, if b is greater than a, we know that this is positive. Think about that, right? It's just a greater number minus a smaller number, so that's positive. So this whole thing equals a negative. What we've just showed is that f of b minus f of a is a negative, or we can say that's less than 0, which is exactly what we wanted to prove right here, that f of b is less than f of a. So once you hold the first two criteria for the mean value theorem, these two were both basically given to us by saying that it was differentiable over x, then the third one holds, and that's the theorem. This is the mean value theorem that we actually use to prove that our function is decreasing. So hopefully that was helpful, and you can see sort of the tie, but why the first derivative test works, that we say, okay, if the derivative is negative, the function is decreasing. It's because of the mean value theorem. Hopefully that was helpful. Again, check out that other video we have on, it's just titled Mean Value Theorem, and you can always send us more questions at info@arnoldtutoring.com. Thanks.